All right, let me talk about this so we can keep things moving along. But let's first go back to ozone. Ozone's O3. Each oxygen is 6, so that gives us 18 electrons. And we want octets. And so we came up with these two. Resonance forms for ozone. Now, there's a minus here, a plus here, and then the opposite. We have to leave the atoms fixed in position. I just don't take a molecule and flip it this way. I leave the oxygens fixed and then just move the electron cloud or move the electron density. But I've been asking people to come up with other structures. So one of the other structures, oops, this is wrong. It's the same structure. One of the other structures that somebody might come up with here is, what if we did a triple bond? Would that have worked? Or two double bonds? Would two double bonds have worked here? Is this a potential resonance form that is just redistributing the electron cloud or electron density? This one doesn't work. Why?
The oxygen in the middle.
Yeah, the octet, the exceeded octet. But let's try to think of some other ways of moving the electron cloud. So let's go with the triple bond here. Drop that electron pair like this. Could this have worked?
Nope.
No, because of the.
Octet in the middle.
Yeah. In fact, this is it. If I try to do other variations of moving electron cloud around or electrons around, it doesn't work. So let's go to N2O. For N2O, we always strive for an octet. And so it depends on which of these you started off with. If you start off with this one, what are the... Well, we could have maybe two double bonds like this. Right? Would that work?
Yeah.
With two double bonds, we have a total of nitrogen's 5, so 2 times 5 is 10 plus 6. This is 16 electrons. And so this has 16 electrons, so everything has an octet. This structure looks good. It's symmetric, but what's bad about this?
Well, nitrogen does not have both nitrogens don't.
Both nitrogens don't have what? Well, actually they do, because when I count the octet, you look at the total number of electrons surrounding it.
But then you have the
Looking at the total number, that's an octet. This is an octet. So both nitrogens have an octet, and the oxygen has an octet because we double count. You know, we just look at the total number. So everything has an octet.
Are we putting the arrows to show like where the electrons are being driven to?
The total number of electrons, let's count that one.
Total number of electrons, 2, 4, 6, 8,
Yeah, they all have
10, 12, 14, 16, 16 electrons.
Well, for the formal charges like that, plus on the nitrogen, plus on the 2 minus 1.
So does it look like this is the best structure?
Because wouldn't the charge for both nitrogen would be positive and oxygen be plus minus? If we do the formal charges?
No, this is the wrong formal charges, but there are formal charges. We should look at the formal charges. Let's take a look at the formal charges here. The nitrogens are not plus 2. The nitrogens are minus 2. It's 2, 4, 5, 6. Actually, not minus 2, minus 1. Minus 1 we just write as a minus. You don't need the 1 there. The oxygen is 1, 2, 3, 4. Oxygen is supposed to have 6. It only has 4, therefore it's plus 2. And this nitrogen is minus. So that's okay. Is that okay? You know, Oxygen gives up an electron here and gives up an electron here. So oxygen gives up 2 electrons. What? Yeah, it's a very, very generous oxygen. Very generous oxygen.
Which is not the case.
Do you think that's the case?
No.
No, I don't think oxygen's so generous. Oxygen is a harsh oxidizer. So the formal charges don't look good. So if we can come up with a better structure, then that would be better. Let's see. Maybe let's go with a triple bond here and a single. So if I do a triple and a single, I still maintain the octet, right?
Wouldn't the hybrid be like a double bond plus a hybrid triple bond?
Well, let's do the hybrid in a minute.
And then that way you'll cancel out.
How about this one?
Nitrogen has over and
Those are formal charges here. Well, let's do this one. What's the formal charge on this nitrogen? 1, 2.
-3.
No. 3, 4, 5.
0.
Formal charge is 0. See, we divide these electrons in half
Yeah.
and count. Divide the bonding electrons in half and count. That gives oxygen and this nitrogen 2, 4, 6, 7.
Got oxygen.
Hi. The oxygen likes the right side nitrogen much more than the left side nitrogen, so it gives up 2 electrons to the right side. Do you think that looks like the case there? In fact, these 2 nitrogens have a fight for electrons, and this one wins 2 electrons, this one gets none.
That was not the case because they both have the
Does
same-
this formal charge distribution look stable to you? No. Is there another bonding arrangement? Can we go, we could go single and triple, but
Maybe
that's it.
a double with a shared with that dotted line bond.
Well,
Or it could be like 1/2 and 1/2.
yeah. Well, looking at these, we could, but we aren't going to do the hybrid yet because these structures don't look so good. These structures look unstable. They look unstable because of the formal charge. The way the electrons are distributed by a formal charge does not look favorable. And so we could try the other skeleton. If we try the other skeleton, we get NNO. And so what are the bonding arrangements here to maintain an octet? We could have a triple and a single. Or we could have 2 doubles. Or we could have a single and a triple. And so this looks like one of the arrangements here. So we'll go like this. 16 electrons here. Electrons here. And 16 electrons here. So we have octets, and you used up 16 electrons. And so are these 3 fine for the potential bonding arrangements, or is there a difference? There is a difference here due to the formal charges. And so let's look at the formal charges here at the top one. The top one, what does it look like?
The center is
0,
1,
1, or just plus,
plus 1,
and
negative, minus.
negative. So the sum of the formal charges is equal to net charge. The net charge on this is 0. You know, the sum of the formal charge is equal to net charge. This is neutral molecule. Nitrous oxide is neutral. How about this one? Formal charge on this nitrogen?
Minus. Plus 0.
0. Okay, let's go to this one. Formal charge on this one?
Minus 3.
-2
Plus.
plus.
So you haven't.
No, you should only get two. You should only get 2 electrons on oxygen.
Oh, do I have, yeah, I'm sorry, I have too many electrons.
Yeah.
What is this one?
Plus one.
Plus. So let's first start off with this bottom one. How stable does that look? Not stable at all. In fact, I'd like to eliminate this bottom one just because the formal charge distribution is all screwed up. Do you see that? And so I don't think it's a single triple arrangement because of that. Now this has lower formal charges, and what we want are lower formal charges because the higher the formal charge, the more electrons we take from one atom and give to another. And so this is good. There are two ways of thinking about this. One way is we have a tug of war for that extra electron. In the top, this oxygen wins that extra electron. In the bottom, the nitrogen wins the extra electron. So if there's a tug of war for the extra electron, oxygen versus nitrogen, who would win? Well, you'd say oxygen would win. Oxygen would win because it has a higher electronegativity. And so we would say this structure is the best. But we would then take a look at the numbers and go, well, oxygen is a 3.5 and nitrogen is a 3.0. And so 3.5 versus a 3.0, is there a significant difference in electronegativity?
0.5.
0.5, is that a big difference in electronegativity? 0.5? A delta En? If you had a delta En of 0.5, we would call that bond nonpolar covalent, polar covalent, or ionic. A delta En of 0.5,
So we covalent. Well, if it's under 2,
Yeah, number is really small, but percentage is
it's on non-polar covalent.
Yeah, what it is.
This one is more electronegative. So we'll have a target more towards
a delta En we would call a bond what? Of 0.5, we would call it a big electronegativity difference or a small? A small. We call it a small electronegativity difference, and it would be close to a nonpolar covalent bond. We saw an example of a delta En of 0.5. HI. Hydrogen and iodine have a delta En of 0.4. Is that a very polar bond?
No.
That means if there's a tug of war between hydrogen and iodine, it's pretty even, isn't it? Right here. Now we go back to this. Even though these aren't bonded directly to each other, there's a tug of war between nitrogen and oxygen. Oxygen's more electronegative, so it should win, but what is the difference here? The difference in strength is 0.5. Is that a significant difference in electronegativity? No. It's not a significant difference. So what happens is this structure dominates, but this structure is also a potential resonance form. And so these are two resonance forms. The reason is because there isn't a huge difference in energy here. Normal resonance forms are equivalent in energy. Is there any energy difference between these two resonance structures? No, absolutely no difference in energy. These are exactly the same energy. But here, these are close, but not exactly the same. But they aren't so different. Like here, there's a huge difference in energy here. This would be highly unstable. Therefore, we eliminate this. Can I say that this one's highly unstable and just eliminate this? And then just give the electron to oxygen? Or is nitrogen going to put up a decent fight? Nitrogen's going to put up a decent fight, right? And so what's going to happen is nitrogen's not going to say, okay, you take the electron, I get nothing. Right? There's going to be some kind of tug of war here. But it isn't going to be a 50-50. like in ozone. In ozone, it's a 50-50 split. And so in ozone, when we look at the resonance hybrid, it's 50-50. This oxygen gets half, this oxygen gets half the electron density. And so it's 50-50. So the hybrid is a 50-50 mix of these two. However, this one is going to be complicated because oxygen is in fact more electronegative, so it should bias this one over this one. And so the hybrid would be, we're going to guess, although we don't know the number, we're going to guess the hybrid is going to be maybe an 80-20 mix. So 80% this one, 20% this one. And so what we end up with is not, let's say this. If it were like ozone, and so we'll do this as an aside. If it were a 50-50 mix of both resonance forms, then the structure would look very similar to ozone here, although the bonding is a little different. And so if it were a 50-50 mix, it would look like this. Where this would be a 2.5 bond. This would be a 1.5 bond. And this would be -1/2. And this would be -1/2, or 0.5. And so that would be a 50-50. But my reasoning is that these aren't equivalent. This one should be slightly lower in energy, slightly more stable. Therefore, I'm going to bias the resonance forms towards that. And so in the hybrid, if I assume an 80-20 split, then it's going to look like this. It's going to be closer to a single bond than it is a double bond, the oxygen here. Closer to a single than a double. If it's a double, it'd be a 2. If it's a single, it's a 1. Since it's closer, an 80% closer, I'm going to call it a 1.2 bond. And this one is going to be closer to a triple bond than it is a double bond. If it's closer to a triple bond, then I'm going to call it a 2.8 bond here. And then the electron over here, rather than being split evenly, I'm going to split it -0.8 on the oxygen and -0.2 on the nitrogen. And so what I did was I made a resonance form that has more of this structure and less of this structure in it. And the reason I put more of this structure is because I expect the negative charge, I expect oxygen to be a little stronger than nitrogen. Not so much so that it dominates. So this is an example where we have inequivalent resonance forms contributing, and this third one doesn't contribute at all. We'll see this in other structures. And so let me talk about one in chapter experiment 9. In experiment 9, you're going to do nitrous acid, HNO2. And a lot of people with nitrous acid like symmetry. They want to keep it symmetric, so they go something like this. But it turns out this is wrong. Acid hydrogens bond to the most electronegative. Atom. And so the most electronegative atom is not nitrogen. The most electronegative atom is oxygen. And so what results is an asymmetric skeleton like this. And then we complete it. When I complete it, I'm going to get this. And then I go, wait, I have a double bond there. I can draw a resonance form for this one. When I draw a resonance form for this one, is this right? No, I'm missing a lone pair. When I draw a resonance form for this one, I might draw it like this, H. So what I'll do is I'll take this lone pair and drop it in the bond. If I take this lone pair and drop it in the bond, I generate this. Does this look good? No, this looks bad. Why? Yeah, because this oxygen here has more than an octet. It doesn't happen, right? But, yeah, let's take, instead of doing that, let's take the lone pair off the oxygen and bring it into the bond. We don't want to take it off the nitrogen. If we take the lone pair off the oxygen and bring it to the bond, we end up with this structure here. Well, how does that one look? This is no good too. This one, look at that nitrogen. Does the nitrogen look good? No, this does not look good. So maybe we can't do that. Well, actually we can. Because if we take this lone pair and drop it in the bond and then kick out this bonding pair and bring it to the oxygen, that works. Well, let's try it. And so what that generates is a structure that looks like this. How does that look? Well, this looks good. Octet, octet, octet. That looks good. And so are these two resonance forms? Of nitrous acid? Well, there's a problem with this one. What's the problem? When I look at the formal charges, are there any formal charges here?
The oxygen is positive.
Yeah, there's no formal charges here. When I look at this one, there are formal charges here. This oxygen is,
Plus.
this nitrogen is, this oxygen is,
Minus.
well, maybe it's the same thing, you know? Maybe I could have two inequivalent resonance forms making my resonance hybrid, and I'll just bias one of them. Maybe what I'll do is I'll just say, you know, I have two resonance forms here, and this one with zero formal charges is more stable, a little bit, and then go from there. What do you think? Should I do a inequivalent resonance hybrid and bias the structure that seems more stable? Well, what do you think of this? Even though this is plus and minus, this does not look good to me at all. Why?
Because the hydrogen, wouldn't that be a positive charge?
Not formal. It has a zero formal charge. We can't start comparing oxidation states. We don't want to compare oxidation states to formal charges. Comparing oxidation states to formal charges, yes, hydrogen has a positive 1 oxidation state, but it has a zero formal charge. And we don't want to compare oxidation states to formal charges because that's like comparing, you know, apples and oranges. And which one has they're totally different. And so this is zero formal charge, this is zero. So this looks very bad to me. Why? If there's a tug of war between two oxygens, which oxygen wins? Which oxygen wins? If there's a tug of war between two oxygens, Well, in this case, we couldn't help but make the formal charge. There was, but in order to get an octet, we had to sacrifice that. Right? That was to make the octet. But in this case, we got an octet here. And so if we do this, that means one oxygen wins, the other oxygen loses. Does that sound right? No, this is terribly unstable. We wouldn't even consider this as a contributor because of that instability. So for nitrous acid, we have no resonance forms. There's only one structure, and this would be it. This is good because there are no formal charges and everything has not cut. All right, so what you'll do is you're going to continue on with experiment 9 and work on the structures.